Let's now examine the relative stability of alkenes, and we're going to do this by looking at the delta H of formation of each alkene. So recall the delta H F of a compound is the enthalpy of formation from its constituent elements in their standard state. So the standard state is 25 degrees Celsius and 1 atmosphere. So if we recall, again back from general chemistry, our understanding of delta H of formation, we see that the more negative the value is, the more stable the compound. And this is because essentially you're giving off, that's why it's negative, you're giving off energy. It's an exothermic reaction, so you're giving off energy. And the more energy that's given off, the more stable the compound is. So if we compare the isomers of hexene to their delta H values in kilocalories per mole, we can see some interesting results that come out of this. So the first one we're going to look at is 1-hexene. 1-hexene has a delta H of minus 10 kilocalories per mole. The next isomer is 3-hexene. So notice I've drawn 3-hexene where the two R groups in that plane are on the same sides. This is how I represent cis, the cis isomer of 3-hexene. Notice 2-hexene and 3-hexene would have cis and trans isomers of one another. The cis stereoisomer of 3-hexene has a delta H, a formation of minus 11.2 kilocalories per mole. And so it's a little bit more stable. Notice the greater the number, or the greater the negative number, the more stable it is. So it is more stable than 1-hexene. And I can compare the cis to the trans 3-hexene, and I see that the trans is a little bit more stable than the cis isomer. Now when I compare that to 2-methyl-2-pentene, I see that 2-methyl-2-pentene is even more stable at minus 16 kilocalories per mole. And then lastly, I'm going to look at 2,3-dimethyl-2-butene, and I see it has a delta H of minus 16.6 kilocalories per mole. So I've basically ranked these in order of increasing delta H of formation, increasing stability. Now, what's the difference? Well, one of the designations that you're going to need to recognize is how to categorize alkenes in terms of their substitutions. So how many alkyl groups are coming off of the double bond? And if we count all of the alkyl groups coming off of both carbons, then we have this designation. You could have one alkyl group, and that's a monosubstituted alkene. And as a matter of fact, the first alkene there, 1-hexene, has one alkyl group coming off of the double bond. So it is monosubstituted. Notice monosubstituted alkenes are the least stable of the isomers. And if I look at the cis isomer, it has two alkyl groups coming off of the double bond, one on each side. So this is disubstituted cis. The trans isomer also has two substituents, two alkyl groups, both of them ethyl groups, coming off of the double bond. It's also disubstituted. It is trans. And then we have a trisubstitute. We have two methyl groups and an ethyl group coming off of that alkene in its entirety. So there are 3 alkyl groups coming off of 2-methyl-2-pentene. It is trisubstituted. And then the last one we see there are 4 substituents coming off of the double bond, so it is tetrasubstituted. And so we see a trend. The more substituted, the more stable. And cis is less stable than trans. And so what you need to remember is 2 things. The first is what we call the degree of substitution. So the higher the degree of substitution, the more stable. And the reason for this is that we have stronger sp2, sp3 sigma bonds that stabilize the alkene. Notice the less hydrogen 1s to sp2 bonds that you have, then the more stable the structure becomes. The other aspect that we have to keep in mind is steric strain. So steric strain simply deals with the trans and the cis isomer, and we see that the trans isomer is more stable than the cis isomer. And the reason for this, again, steric strain. So if I take a look at this the structure of a cis isomer where I have two R groups that are on the same side of that double bond, those two R groups can bump into one another, and therefore there's steric effects that are associated with that, making the cis isomer, stereoisomer, higher in energy than the trans isomer, where the two R groups are on opposite sides of one another and they can't bump into one another. Therefore, trans isomers are more stable than cis isomers. This has great ramifications all throughout biology, and we'll get into that later on. But what you need to understand is the more substituted an alkene is, the more stable it is. And trans isomers are more stable than cis isomers based on steric strain.